Okay, cool. We'll be starting now. The first lab of the school will be on virtual screening. We are quite lucky today to have Zhu and Cas Wognum. I'm not sure I'm pronouncing that right, but yeah. And Lu come with 6 years in experience in AI for drug discovery. She has her PhD in machine learning application for biological systems. And Lu, and I'm sorry, that's Lu. And Cas is a computer scientist by training and a ML engineer at Valence Lab. Thank you both for doing this. And without further ado, let's welcome the speakers.
All good? All right. Good afternoon, everyone. So welcome to the very first lab. Just to reiterate, I think the goal of these labs is really to experience with sort of easy to follow along practical examples. We only have so much time. In practice, you'll find that there's a lot of nuance that we are not able to cover right now, but we'll do our best to just sort of convey the main ideas and to get you started. Yeah, so a little reminder of the agenda that we had set out for today. We might deviate a little from this based on how many questions there are and et cetera, et cetera. But we'll start off with like a short introduction. This should take about 30 minutes. It's just to sort of set the stage for what we'll be doing in the practical example. Then we'll have a 30-minute break, after which we'll immediately start with like a code example that you can follow along with. All of those resources should be shared through Portal. What I would advise you to do is, if you're interested in following along with the code, actually running the cells, maybe making some changes as we go, try set everything up during the break. We offer like a Google Colab link you can use to get started. But the Wi-Fi, I think, has been a little spotty. So just my advice is just give it a look during the break to make sure you're all set up and can follow along if you're interested in that. And then at the end of the day, we'll do like a short recap to just sort of summarize everything that we've done and any further directions in case you're interested. All right, so today we'll be talking about virtual screening. And the motivation for virtual screening simply is to get to better molecules faster. Now, that's a very simple statement, and there's a lot of complexity behind that. And actually, even the definition of what makes for a good molecule really depends on the specific program you're running, the type of medicine you're after, the target that you're targeting, the protein that you're targeting. So this is not an easy question to answer. However, typically, in a drug discovery program, you'll come up with a set of experiments that you'll run that will tell you whether a molecule is good or bad. And there's multiple of these experiments you can do, and you're actually optimizing for multiple properties simultaneously. So that's quite a complex task. And you can see that there's I put some prices on the slide just to give you sort of a hint of like what we're dealing with here. So you can see the prices range, like there's quite a big range of cost, and these are the costs for like a single molecule. The problem is that we won't be doing this once, like we won't be just taking one molecule and we'll take it from start to finish without any failure. No, in reality, there will be lots of failure along the way. So we'll actually have to do these experiments many times. And that's one of the things that creates a lot of costs within drug discovery programs. Okay, so where does virtual screening come in? Virtual screening is actually, I would say, a relatively straightforward application of machine learning within drug discovery. The idea is, rather than just always running these experiments, maybe what we can do is we can build these machine learning models that can predict the outcome of the experiment. And we just predict those properties for a large set of molecules, and we'll only actually push the very best molecules coming out of that virtual screen. We'll push those to the experiments, sort of better leveraging the capacity that we have available to us. Okay, so I already said, I think virtual screening is a relatively straightforward application of machine learning. If you've done any sort of like property prediction, classification, regression within machine learning, you'll find that a lot of the same sort of design decisions apply here. However, I would say that there's actually, in drug discovery, generally speaking, not just in virtual screening, we'll see that there are few straightforward answers. What's best practice really depends on the specific program that you're running, the downstream application that you have in mind. And again, we won't be able to cover all of that complexity within this 30-minute slot that we have just to introduce it, or not even within like the practical session afterwards. But I just want to really bring this point across. First example of like how this might look like, but in practice, there's a lot of things you'll have to consider to make sure you actually have an impact on a real drug discovery program. All right, so before we dive into the exciting science, before we dive into the exciting technology, I personally always think it's important to take like a little step back and to remember that in the end, we're doing this to radically improve the lives of patients, right? And also within this running example, we'll be focusing on a protein called EGFR, which is involved in lung cancer. And lung cancer actually is the biggest cause of cancer-related death up until today, I believe. So this is the starting point. And one of the reasons I like to bring that across is there will be, if you're actually involved in a real drug discovery program, there will be a lot of like failure along the way. There will be a lot of like roadblocks, a lot of obstacles, a lot of frustrating times. So I think it's just important every once in a while to remind ourselves what we're ultimately doing it for. So little intermezzo, we'll get back to the science right away, but I just personally find it important to just bring that point across. And I think right away, we'll see some of the complexity come in. So I just mentioned this like lung cancer because it's intuitive. It's nice to understand. Everyone has a sort of vague understanding of what that means or what the consequences are. But in terms of, if you're talking about biology, lung cancer is not a single disease, right? There's a lot of nuance here. So you have lung cancer, then you have non-small cell lung cancer, and then you have different types of non-small cell lung cancer. And we will be looking at a specific protein throughout this like practical example that is involved in one of these specific types of lung cancer, and that protein is called EGFR. But we'll be looking actually at a specific mutation of EGFR. There's multiple mutations, and all of this information is important. And we'll also actually be looking at a specific binding site of EGFR. And again, all of that information is relevant. So if you were hoping to like solve lung cancer in like a 1.5 hour lab, I have to disappoint you. I don't think that's entirely realistic. Yeah, and look, I'm no biologist by training, so I'm not the best to talk about this, but I just want to really bring across there's just a lot of nuance, a lot of complexity. Okay, so EGFR, why are we using this example throughout the practical sessions? Well, there's a couple of nice, it's a well-studied protein, so there's a lot of information available about it. And for the sake of this like practical lab, there's two things that are specifically nice. One is that we actually know the 3D structure of the protein. So we have a good understanding of like what it looks like in 3D space, which is not a given for any protein out there. And the second is that there actually are drugs that have been developed, and there's a lot of experiments and a lot of molecules that have been tested against this protein. So we also have some chemical matter that we know has some effect on this protein, which is also an important starting point for today. Okay. So then virtual screening. So I explain the intuition behind virtual screening, but here again, there's a lot of complexity and nuance. So virtual screening is not a single technique. At a high level, there's two categories, either structure-based virtual screening, which you should hear more about in tomorrow's lab. The assumption that structure-based virtual screening makes is that you know the 3D structure of the protein beforehand. And then there's ligand-based virtual screening. And in ligand-based, you assume that there's a set of molecules known to have some sort of interaction with the protein. So as you'll see, these two approaches are complementary. Based on, again, your specifics, you might use one or the other or both or neither. It really depends on sort of your setup. And then it's also worth noting that within each of these categories, again, there's like subcategories. So there's more different techniques to actually then implement these ideas. We'll be looking at QSAR modeling. But I'm saying this a lot, I find, but just want to bring across that each of these topics that I just sort of briefly put on the slide is a whole research direction on its own. And if you're interested in any of it, I invite you to look into that. Okay, so QSAR modeling, we're finally getting sort of close to where we want to be for the context of this lab. So QSAR modeling stands for quantitative structure activity relationship modeling. I think machine learning is a very straightforward application, QSAR modeling is a straightforward application of machine learning. But I do want to say that this is a topic that has been around for quite a while, and there is techniques outside of machine learning to apply these, to implement these ideas. So what we'll be doing is we'll start off by selecting a screening library there on the top right. That screening library is just a large, diverse set of unlabeled molecules, typically something that we can easily get our hands on. So it's not something we have to synthesize manually ourselves because that delays things. It's typically something we can buy off the shelf or have in-house within the company. Then what we'll do is we'll also look for a data set that for the property of interest that we're trying to model. So if we're looking against, for example, binding affinity against a specific target, we'll try find a binding affinity data set for that specific protein. And what we'll do is we'll, using that data set with labeled examples, we'll train a model to sort of predict the outcome of that experiment. And modeling, I think, as you've seen throughout the day, through the talks, there's a lot of things we need to think about here, such as the featurization. How do we split our data set in a train and test set? What's the algorithm we want to use to sort of optimize? And what are the metrics we use to evaluate performance? All of those things are important here, but I would say if you're familiar with machine learning, those should sound familiar. And then the last thing we need to do is like, okay, so now we've had this model, we have the screening library, we predict the property of interest for all of those molecules in the screening library. And then the next question is, how do you actually prioritize the results that you've been given? If you have just a single property you're predicting, that's relatively straightforward. But what we'll see is you're not optimizing just a single property, you're optimizing multiple at the same time. So if there's no molecule that does best on sort of all axes, how do you then choose the molecules that you want to push to the experiments? Okay, so starting off with the screening library. I think this is maybe the most simple part, or maybe that's just my own personal lack of expertise, but in my experience as a machine learning engineer, I think this is typically the simplest part of like the problem. There are a lot of like readily available screening libraries. For example, enamine, the real space, I think here on this plot, it has about 4 billion molecules. This is growing exponentially. I think the latest I've seen is 48 billion. So that's an enormous set of molecules you can buy off the shelf that enamine sort of guarantees you they can make relatively quickly. Yes, these screening libraries can also be in-house. If you're talking about big pharma companies such as Johnson & Johnson, they will have their own, typically, they will have their own screening libraries ready to go in-house to screen against. So I was saying like the real space has about 48 billion molecules, I believe, at the moment. Once we start operating on that scale, there's a lot of like computational challenges that we'll run into. So for the sake of practicality, we'll be using a different screening library, which is the hinge binders one. I don't want to go into too much detail, like why that is a good choice, but just to sort of briefly explain that, this library is specifically designed to target proteins such as EGFR within a specific binding pocket. Again, a lot of nuance I can't cover, but it's a good choice for finding starting points against EGFR and similar proteins. Okay, so then the data set. I think if you look at these numbers just on the slides, you might be like, wow, that's amazing. We have so much data we can use to model. So Pupkin and Campbell, they are data that are, I would say, not really data sets. They're like databases that aggregate data from multiple different sources, typically public. So that typically tends to be data from research papers, data from patents, public sources like those. That does mean that it aggregates a lot of things into like one place. That's nice. You can access it through a single like interface, but the data set that you actually end up with is very heterogeneous. So if you're looking at a specific property of interest and you want to make sure that the conditions of the experiments are similar and that everything sort of like is consistent within the data set that you're generating, you'll typically work with way smaller data set sizes in this. So what do I mean with way smaller? I think Lou and me, we have been involved in programs where you start off with just 200 molecules. If you're lucky and you're using a more known target, maybe you can get 1,000, maybe 10,000, but that's really like hundreds. Then there's other problems with these data sets. That's that typically they are imbalanced, they're expensive to generate, so you can't just sort of get more data if you need it. And they're also subject to experimental noise. And all of these things further complicate our lives as machine learning engineers, because those are all things we have to tackle, which maybe you don't have to tackle when you're working in computer vision or natural language processing, or at least not to the same degree. Okay, so now we have our data set, we have our screening library. Next question is, how do you want to featureize things? I don't want to spend too much time on this. I know there was a whole talk about it earlier today, but yeah, just want to say again that like it depends. We don't, at least like the search for like a universal molecular descriptor that sort of captures all the richness of molecular information is very much still ongoing. So depending on your use case, you will want to try different featurization schemes and sort of see what works best. Yeah, I think that's the main point I want to bring across here. Okay, then splitting. So we want to make sure that our model doesn't just memorize the data set. We want to make sure that it actually generalizes. The way to typically do that in machine learning is you split your data set in a train and test set. You use your train during method development, and you use your test set only once at the end, ideally only once, to evaluate model performance. So the question is, how do you split that data set in a train and a test set? And again, this is not a solved problem. It really depends on your downstream application. It depends on your use case. So for example, if you're in a scenario where you're optimizing a chemical series, so typically in drug discovery programs, you find some starting points and you start making small tweaks to the starting points to try sort of improve the activity profile that you're after. In that case, you'll get like a chemical series, is what's called. So it's like a lot of like very similar molecules. You stay very close to the sort of the starting point. In that case, maybe a random split is fine because your model doesn't need to generalize to like the other part of the chemical space. So maybe that's fine. However, if you're optimizing a chemical series and you're hitting like a limit, you can no longer optimize it any further. Or maybe you're in a patent space, so you cannot actually, even if that molecule looks perfect, it might not be something you can bring to the clinic because there's some other company holding a patent on it. In that case, you will have to get to another part of the chemical space. And one of the techniques to do so is called scaffold hopping. So in that, and again, I can't go into too much detail, but like a scaffold, you can think of it as the structural core of a molecule. So in scaffold hopping, what you're trying to do is you're kind of to sort of try to swap out the structural core of the molecule for something else while maintaining the activity profile that you're interested in. If that's the scenario you find yourself in, a random split is probably not going to give you an accurate estimate of like performance. So what you want to do instead is you want to maybe do a scaffold split. I deliberately say maybe a scaffold split, maybe a random split, because again, it really depends. It depends on your target space as well. There's just a lot of considerations here. Okay, so method evaluation. So we've everything up until this point we've done perfectly. We've done everything that's expected of us, and we get our results back, and yay, happy machine learning scientists. We have a 1% improvement over state of the art. That's it. We've just solved drug discovery. That's of course not how it works, because then the domain experts will come in and they'll ask you all sorts of annoying questions, such as what's the statistical significance of those results? What's the applicability domain of your model? What's the decisional impact of this improvement? Those compounds, they look nice, but there's no way we can synthesize them, so forget about it. How did you handle stereochemistry during dataset curation? Could you explain the predictions, right? Interpretability is something that was brought up earlier at the last talk, or the 2 talks back. And even questions such as like, how do I install your model? This may feel a little silly if you have a computer science background, but you know, you're working in interdisciplinary teams. It's important that the people you're working with, that they trust your predictions, but they also sort of have an intuitive way of using these methods. So all of this becomes important. And I don't expect you to understand everything that I just sort of like quickly put on the slide here, but I think that's precisely the point. You'll run into a lot of things that as a computer scientist, people have never really asked you. And now all of a sudden it's becoming very, very important to address all those topics. Okay, so then method evaluation. So we have a way to evaluate our method, but then the question is, what about method comparison, right? Like, there's other people that have proposed methods before us. Are we doing better than them? Yes or no? This again is something that it can get tricky. I think what's important to remind ourselves of is that machine learning models, the whole process of training a machine learning model is subject to multiple sources of uncertainty. The specific split you use to train your model, maybe the specific, or no, not maybe, the specific data set you use to train your model on, like all of these things introduce some stochasticity, difficult word, some randomness into the process, and that means that it's important in our method comparison to verify we're seeing our structural, but it's something that will generalize to other data sets and other like model seeds, or whether it's just something that's due to chance, right? If I train 1,000 models and there is some variance in the results, chances are that I will find one that does better than existing methods. Is that really a valuable improvement? Probably not. So this is, again, something that's important. I would say this is important in computer vision and natural language processing as well, like other like typical domains of machine learning. However, the difference is we're working with very different types of data sets. The data sets we have are smaller. They are noisy, they are imbalanced, they're heterogeneous, and all of that sort of increases the variance of the results. So it's extra important in machine learning for drug discovery to make sure your results are reproducible. Furthermore, you're working with interdisciplinary teams, so it's important that what you're saying is actually what sort of happened, or that there's a high probability of like the conclusions you're conveying to the rest of your team is what actually plays out in practice. It's important to build trust. And then finally, you're operating in a high stakes application, I would say. So like these model predictions, they're not, well, they inform costly experiments. So you want to make sure that if you're proposing a new method rather than another, it's actually better and not just you saw one random seed that happened to do better, but cannot really reproduce that in a real life setting. Okay, so then we've deployed our new model. It is doing better. We're getting predictions for all these molecules. And then the question becomes, okay, how do we want to prioritize this? And as I was saying, typically you do not optimize one property at a time. Typically you optimize multiple properties at a time. And chances are, if we look, sort of like plot these two properties on a two-dimensional axis like I'm doing here, there won't be one molecule or a set of molecules that is clearly the best on both cases. What you'll more likely find is what is called like the Pareto frontier. So it's this sort of like edge in the property space where you cannot improve upon the molecules by simply moving in one direction. So the whole question of prioritization is there a way to select molecules that we are optimizing for multiple properties at the same time? But then there's also some practical concerns. You want to minimize the risk of your chemical program. So you probably want to have diverse starting points. So if you wanted the set of molecules that you're going to run through your assays, you want to make sure that there's some diversity in that selection. It's not all sort of variations of the same molecule. Furthermore, you can think about topics like active learning. So maybe I want to spend one cycle to generate some data to really improve my model so that in the second cycle I can expect even better results. If that's the case, how do you go about selecting your molecules? Do you want to like include some sort of uncertainty estimate? All of these are questions you'll run into. Okay, so we've done sort of like a high level, quick rundown of what QSAR modeling is all about and all of the little exceptions and special things we need to be mindful of. This is actually, we'll in the practical session after the break, we'll actually implement a simple version of this loop, of this cycle. Again, we'll not be able to address all the nuance, but we'll leave some like comments in there. So if you're curious about this topic, you want to explore it further, there's some like homework exercises you can explore and to continue exploring this topic. That's all I had to say for the introduction, I think. Yes. If there's any questions, I'm happy to take them now. I also want to let you know that there is a space on Portal where if you're more comfortable or you just don't find the time to come chat with us now, you can pose your questions there. We'll make sure to go through them and answer any of the questions that are open. Yeah, and then just one final thing before we head into questions, just want to repeat that if you want to follow along with these examples, you can just spend a little bit, like 5 minutes during the break to set up your Python environment or your Google Colab or anything you need so that you're not lost in the first 5 minutes of the practical session. All right, any questions?
Questions?
Sorry.
Sorry, I just had one about the tutorial. Is it something that we could run locally by setting up a Python? Oh, okay.
Yeah. So we also have notebooks that you could run locally. Did we share did we share access to the GitHub already?
The GitHub is public. Maybe we can share the link. We can put the link on the screen during the break. So
Yeah.
everyone can have access to the GitHub and run it and use it.
Yeah, so you will be able to follow along locally.
There was a hand
Yeah,
raised
here in the front.
in front.
I just mean it's collab file. You have a collab on GitHub.
Yes,
Yeah, we have
we
Colab
also
too.
have a
Yeah.
a collab set up so we can follow along on collab, download locally, whatever works best for you.
Okay, cool.
Cool. With that, let's break now, and we'll be back in 20 minutes. Thank you.